All right, anyway. And then, oh wow, we got 9 people here, that's awesome. And I'm a no mask teacher, Joel. You're gonna stay 6 feet away from me, so if that upsets you, you're welcome to go. Caleb. Their cards on top. All right. Okay. So, first and foremost, I do not have the answer to Drew's question from last time, but I promise I'll have it next time because he's going to email me to remind me about it versus me being reminded about it 5 minutes before class. At any rate. All right. So, as promised, we're now going to talk about material which is more near and dear to my heart. Hopefully you can sense it in my delivery. I don't know, maybe not. But so I wrestled back and forth with what to talk about first. And I thought about talking about groups and representations and Lie algebras and stuff like that, but it turns out there's one little ingredient in that story which really made me want to talk about space and space-time first. So we're going to talk about space and space-time first, and then we'll eventually transition into the stuff in due time. So we're going to start out by talking about space and space-time. And that's the title of this topic, although today we'll really just talk about space. We will in due time add time to the story to make space-time. Okay? So, I'm not going to write this, I'm just going to read it to you, but often in physics, students are exposed to a limited and often wrong perspective by staying in the simple landscape of 3D space that is flat. Okay? Many of you have done much of the physics that you've done in 3 dimensions, assuming that it was flat. And this has led you to accept a lot of conclusions which in a more generic case are absolutely false. For example, you might believe that spinors, you remember those?
I do.
Okay, you might believe that spinors are smaller than vectors. Spinors, 2-component, vectors, 3-component, right? Turns out that's wrong in general. You might have the impression that a cross product gives you a vector. Nope, that's not true. You might have the idea that the sum of the interior angles of a triangle is always 180 degrees. It's not true either. That the shortest distance between 2 points is always a straight line. That's not true either. That a Klein bottle must always intersect itself. Nope, doesn't have to. And that you can spin around an axis. That's a well-defined operation. That a magnetic field is a vector field, just like an electric field is a vector field, so too is a magnetic field. It's not true. And lastly, but perhaps most importantly for our discussion today, that vectors live in space itself. Right? I mean, that's what we're used to. You know, if I'm driving a car, I got a velocity vector. That velocity vector lives in the space that the car is moving in. Done. Right? Turns out no. Okay? So in order to sort of address these misconceptions, what we have to do is we have to loosen up that rigid 3-dimensional flat space framework, and there's various ways to do it, okay? Number one, you can always add time to the picture, non-trivially of course, okay? In our more traditional perspective of the geometry, you know, based on Euclidean space, we have 3 flat dimensions, and then time is just this sort of extra thing. It's not a part of the 3-dimensional space. Technically, you would argue that that space is a 3-dimensional vector bundle over a single base of time. We're not going to do that though, because if we're going to integrate time into the story, we should really just fold it in as relativity has taught us. And it turns out if you relativize time and add it with the spatial dimensions, then some of those myths that I was talking about will be upturned. Another way to upturn some of these is to gently curve the space, okay? Turns out working in flat space makes a lot of things really boring. And if you just even gently curve the space, suddenly a lot of the misconceptions will be cleared up. Another thing is, of course, to consider moving out of 3 dimensions into 4 dimensions, 5 dimensions, 6 dimensions, whatever, okay? Chances are if you change the number of dimensions of space, okay, then things might, reveal themselves. But last but not least, if you just study the 3D flat space carefully, okay, if you do it really carefully and think hard about what you're doing, then that itself can reveal some of these misconceptions, okay? And to be honest, this is not just me exploring these interesting possibilities in order to unearth these untruths, but rather the physical universe is like this, right? Time is part of the space-time we live in. Space is curved. It's not flat. It's approximately flat, but it's definitely curved. And according to string theory, at least, there's a chance we might have some extra dimensions, okay? So there's physics-oriented possibilities for all of these. And so we're going to consider unearthing some of these rumors. So to begin, we're going to consider the simple case of R3, okay? And the first question that I would like to ask, and I'll ask Matteo. Matteo? 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 No Matteo. All right, I won't do that with Hunter. Solomon, or Caleb. I know Caleb's not here, at least email me. Matthew. Matthew, is R3, is it a space or is it a vector space?
If we're loosening our descriptions a bit, I'm more inclined to say just a space.
Mm-hmm.
Yeah, especially if we're going to be curving the space. The idea that a vector can sit in our definitions of a vector along in this space and exactly flush with the space is just not going to work.
Okay, so anybody want to argue with him? I mean, yes, if we curve the space, then it's no longer flat like R3. But if we consider R3 itself, so forget curvature for a moment, if we're just considering R3, does R3 constitute a space or a vector space? Any other takers? Who says both? Does anybody know the difference between a space and a vector space? Okay, let me give you the definition and how R3 can serve as either, okay? So first of all, let's think of R3 as a vector space. All right, and just to give it a name, we might call it E. Okay, where the word Euclidean comes into play, R3 is generally called Euclidean, but whether you're dealing with a vector space or not, we'll just indicate with the little arrow. But thinking of R3 or a Euclidean vector space, what we could imagine is we pick a point in the space, okay, and based on that point, we might construct a coordinate system just to label things. All right. Now, this point here is important because this thing is going to define for us the very special zero vector, which plays a crucial role in the definition of a vector space. Okay? Do you remember the definition of a vector space from the first day of class? One of the important defining properties of a vector space is that if you take the zero vector as the identity, then the vectors form a group under addition. Okay, that's a defining property of a vector space. You can add vectors together and you'll get other vectors. Zero plays the role of the identity. The zero vector plus any vector gives you that vector back. Okay? Now, other vectors by basically picking, oops, picking a point and then constructing the vector which goes from the origin to that place. Okay. And then if we pick another one down here, okay, notice all the vectors in question have their tails at the origin, okay? But along with this comes that defining relationship of vector addition. Because what can we do? We can take this vector if we want, and we can just slide it up so that its tail sits on the tip of this one. Okay? And then we just say, all right, fine, the sum of these two is given by that vector. This is R1 plus R2, which is another vector in the space. Okay? Now, notice also that we can give a vector its magnitude through the inner product, and I'll just say one again. Okay. All right, so this is considering this space as a vector space. Now what I would like to do is I would like to instead consider it as a Euclidean space. Which we'll call without the vector. Okay? So, as a space, we imagine that this is a collection of points, okay, which we can describe by defining a coordinate system. There's nothing that's wrong with that, so we'll just define a coordinate system. Okay? Now, one of the very, very important things about identifying this as a space versus a vector space is that in a vector space, the origin plays a crucial role. In terms of a space of points, a collection of points, if I'm going to put a coordinate system on it, does it matter where I put the origin? No. Okay? It doesn't at all. Okay? So, all right, fine. But I mean, I could just pick a place and then there's an origin. So maybe I could just call that the origin. But here's an interesting question. Does it make any sense to take this point and add it to this point? Does that make any sense? No. The sum of 2 points makes no sense. Notice the sum of two vectors, perfect sense. Sum of 2 points, no sense at all. Okay. What about the length of a point? Does that make sense? I mean, P1 plus P2, no sense. What about the magnitude of P1? Does that make sense? No, no sense. I should say equals no sense. Okay. Is there anything I can do with the space? Yeah, I can refer to the distance between 2 points. Okay. So I can take P1 minus P2, and that defines this guy, which could have directionality depending on the order of the subtraction. Okay. But moreover, this will be accompanied by some definition of length. Okay? So, we have R3 can be a vector space, or it can be a space, Euclidean space in particular, where we're talking about a collection of points, and we can just so happen to use a coordinate system to describe it. Now, the question I might ask is, if we're talking about velocity, this is just a simple example of a vector. If we're talking about velocity in three flat dimensions, does velocity live in the space you live in, or does it live in a vector space? I mean, velocity is a vector, right? Right? So it needs to live in a vector space. But the vector space is not the same as the space, the collection of points. Does that make sense? Okay? Now, here's one fix. Here's one way to fix it. Okay? Here's a way to fix it. What we can do is at each point in Euclidean space, in E, we designate the origin. So what I'm doing is I'm picking a point in E, and I'm saying this is going to be the origin. Okay? And then we use subtraction, and I might call the origin A. And then we use the subtraction of all other points minus the point A, which we're calling the origin, okay? To define a vector space E, okay? So what we're doing is we're taking this space, we're picking a point and we're saying, okay, fine, I'll do a coordinate system, I'll choose the origin, and then I'm going to create vectors by taking all of the other points in the space, subtracting them, or subtracting from them the origin point, okay, because that's well defined in a space, and then calling those differences vectors. Okay, they've got magnitude and direction, just like a vector does, okay? Well, there's one more thing we need to do. It's small, but we can do it. We need to do this at every point in the space. So you can start drawing your vector space. Let me know when you're done. Okay. So we want to do this at each point in E. Okay? This results in an affine space. Okay? Over the reals, it turns out, but it's not important. Okay, now I'm not going to hang myself up on affine because this is one way of sort of resolving this, but it's not the best. Okay? But at least now we can answer the question, if a car is driving down the road in space, where does its velocity live? It lives in the vector spaces, which are constructed over each point in the space. Okay? So clearly, what I'm trying to get at is we have a space that we move around in, and then we have a vector space, which sort of kind of sits on it in this weird way, but we'll generalize it in just a moment. Vectors live in the vector space. Things move in the space, okay? Now, while this works, it fails in general. Let me give you an example of the failure. So we're going to consider a curved space, the simplest curved space, that being an S2. So, yeah, I'll just do it here. Okay, so consider S2, which hopefully you're all familiar with the idea that S2 is the surface of the ball. Okay, so S2 is a two-dimensional surface that is hopefully obviously, but maybe not so obviously, it's obviously curved. Okay, and it turns out this is the simplest setting in which to explore a lot of these issues. So we can ask ourselves, is this a vector space? Okay. Notice R3 could count as either a vector space or a space. Now I'm considering a different collection of points, those that create a surface of a sphere, S2. This is obviously a space, but can it be a vector space? You guys are so quiet. Chloe, give me an answer. Yes or no?
I'm going to go with no.
No? Wow, that's so brave of you. Okay, the correct answer is no. Let me show you why. Well, first of all, let's think about how we define a vector space. So if I take the vector space and I say, okay, I'm going to define this point as the origin. It's arbitrary what point I take as the origin. Then I might say take this point R1, this point R2, and then I might construct the vectors which point towards them. Okay. Well, they're curved. That's kind of weird, but what I really want to know is, can I add them? Can I add them? Can I add these two and get a third vector? Okay. Well, how do we define addition here? How do we define it?
Tip to tail?
Yeah. Yeah, we went tip to tail. And it doesn't matter which, obviously. We can move either this one to here or we can move this one here. We'll get the same answer. But this means that I'm taking at least one of the vectors and I'm moving it. Okay? Huh. Okay, let me actually simplify the situation here and colorize it. So consider for a moment that we're going to take this small vector which points in that direction. I'll call that one R1. And then we'll just take a long vector that goes from here down to here. I'll call that R2. Okay? So what I would like to do is I would like to add R1 plus R2. Now, I've got to move one of them, right? So we'll move the little one from here down to here. And then we'll just draw the tip to tail thing. We're done, right? Okay. Well, I have a question. Here, when I move this from here to here, does it matter how I move it? I mean, can't I just go like that? Or can I go like this? Or like this?
You definitely did the last one.
Yeah, no, the path shouldn't matter, okay? So let's take two different paths. Let's take this path. And let's take this path. Okay? Both of those paths begin at the origin and they end at the tip of this vector. So if I move this vector along either of these paths, when I get it here, I can then add them together, right? Well, let's do it. I'm moving a vector along this path, and I think one thing I can imagine is if I'm going to move this vector in any path to get to here, I should keep the vector parallel with itself. right? Now, if I do my best to keep the vector parallel with itself, then I can imagine that the vector would go like this, because remember the vector lives in the space. And then I'll just pull it around here, and there, that's what I get. So now I can just add this vector to this vector, and I'm done, right? However, if I take it along this path and keep it parallel to itself, I get a different result. This means that if I want to interpret this as a vector space, the sum of two vectors depends on the path you're using to put them tail to tip. Maybe we should pick out a special path? No. This is not a vector space. Okay? It's not a vector space. But it's clearly a space of points. So it's clearly kind of playing this role and having all this adventurous stuff, but it's not satisfying this. So, well, let me ask you something. Can a car exist on the surface of a sphere, S2? Yes, it can. Watch. See? Cars exist on the surface of S2. Cars can go. They have velocities. They have velocities. Where does a velocity live? Does it live in S2? Nope. S2 is not a vector space. Can we save this by taking copies of S2 and gluing them all over S2 to create an affine? No. This cannot serve as a vector space. Okay? So how can we fix it? Well, it turns out that what we can do is we can take this curved space, S2, and we can pick a point. And to that point, we can affix something which can definitely be interpreted as a vector space. Duncan, what would I affix to this point? What would I attach to this that allows vectors to exist?
Origin?
Well, I mean, affixing an origin doesn't help me because if vectors are defined in the space, moving out from the origin, they're suffering from this addition, lack of addition. I'm actually going to increase the space. It's going to get bigger. So what would I attach to it?
An extra dimension?
An extra dimension? It's a two-dimensional space. How many components does vectors in 2 dimensions have? 2. So how many extra dimensions should I be attaching?
2.
2. What geometry should they have? What geometry admits vectors?
A plane.
The plane, R2. So at this point, I can affix a plane, which is just R2. Okay? Now, a plane attached to this point, that can, you can put the plane in any direction you like, right? I mean, it's just a plane, and all it's got to do is touch this at one point. However, hopefully, and I won't go into the details of it as I did in my general relativity class, hopefully it's fairly obvious that there's one preferred orientation in contacting the plane with the sphere, and that is what?
Tangent.
That it be tangent to the sphere at this point. Okay? This is called the tangent space if something is moving as it encounters point P, the direction of its velocity as a vector would point in this plane. Now, this looks a hell of a lot like what we did earlier, right? In that affine thing. Except that the geometry we're attaching is different than the underlying geometry. But there is a much bigger and better problem, or advantage, I would say. In that affine construction, you could literally take every vector space that you're tacking into this space, and you could just put them all in alignment with each other. So that you could really, in principle, just define one huge coordinate system and just say the origin's moving around. That's the affine construction. You're basically saying, yeah, I just want to let the origin be undefined. At any point, I can fiducially call that the origin and then construct vectors. But here, notice, if I take the point Q, the plane tangent at Q is not in any way, shape, or form the one that is tangent at the point P. So again, in flat space, if I want to affix a vector space to each point, all of those vector spaces can be aligned with each other. They don't have to be, but they can be. Okay? And then once again, you can adopt a single large coordinate system and just move the origin around. You can't even do that here. The vector spaces are not parallel to each other. Okay? Well, if I assign tangent spaces to each and every point, then this gives rise to the tangent bundle. Over the space S2. Okay? All right. Now, we have, at long last, taken a non-trivial, in fact curved space, and we have allowed ourselves this additional construction, which now allows the existence of vectors on S2. Yes?
So we have defined the tangent space to be the same dimension as the space that we're putting it into.
Yeah.
Why couldn't we just add one dimension and then unify all those spaces by just setting R3 and defining vectors at each point that can only start on S2?
Well, first of all, you're imagining S2 embedded in R3. You don't have to. There doesn't have to exist in R3. And many spaces, I could ask you about an S5. Can you embed an S5 in R3?
No, but you could embed it in R6.
Sure.
I guess it depends on the topology.
So, yeah, there's a lot of simplistic ideas you can do for the embedding of these geometries into R3, but we want to very quickly get away from that because most of the spaces, which especially the ones we study in GR, can't be embedded in a larger space. Okay. All right. So the fact that we can do this construction with a two-sphere hinges radically on two-sphere having a certain property, that is S2 is a manifold. Okay? And a manifold, in essence, is a space of points that locally resembles Euclidean space. Near each and every point on the space. Okay? Now what do I mean by locally? Euclidean space is flat. Okay? And I know I'm using the words flat and curved, and I don't want to go through the rigorous definition of measuring that and finding out about it, so forth and so on. But, hopefully it's obvious that this, and by the way, 3 dimensions you might have a hard time with, but if I just think of 2 dimensions and a flat sheet of paper, that's clearly flat, okay? So 3 dimensions is just a 3-dimensional extension of that, okay? While S2 is clearly curved, all right? Now, don't ask me about a circle right now, because it turns out that's flat even though it looks curved. But anyway, more on that later. All right, so, however, if your curved space is a manifold, then what that means is that if I pick up any point in the space, any point, it doesn't matter which point I pick, if I zoom into it close enough to the point, then in the neighborhood around that point, and that neighborhood can be infinitesimally small if needed, the geometry will look flat. Okay? Now, if you are bothered by that notion on an S2, think about living on the Earth. Do you regularly experience the fact that the surface of the Earth is curved?
It's not.
I know, well, we still got to fake.
It's just, as you go close to sea, it's all flat, so that's.
Yeah, I know. At any rate, no, but, okay, fine. Throw this physics out the window. Let's just go back to GB and do it. Anyway, so no, on the surface of the Earth, obviously, we're a very small neighborhood on this really large sphere, and for the best approximation, we can say the space around here is flat, okay? And I'm not talking about the curved space of general relativity, I'm just talking about whether the surface of the Earth is flat or not. Locally, it looks flat, okay? Let me give you some examples, just to sort of drive this point home of what is and isn't manifolds. So we'll start out with a set of manifolds. First of all, any flat space, and it doesn't matter what dimension I use, Rn is a manifold. We can do a circle, S1, that's a manifold. We can do a 2-sphere, that's a manifold. Or we can do a torus, or a donut, T2, that's a manifold. There are many, you can go higher, you can go to higher dimensional spheres, higher dimensional tori, you can do more complicated things like labials and so forth. Now let's look at some examples of not manifolds, just to drive this point home. First and foremost, if the space I give you has boundaries, say I'm considering the line segment as the space, this is not a manifold, okay? Okay, that's fine. What if I just give you an infinite space, but I give it with a little bitty sort of weird point? So the surface of an infinite cone, it doesn't have a boundary per se, but this point is definitely kind of screwy. Okay, that's not a manifold, and neither for that matter is figure 8. Okay. If you imagine in the interior of this is very much like a manifold. I can pick any point and it looks flat, but at the boundaries is where I run into problems. Similarly, everything is fine here except that boundary, and then here too, everything's fine except that intersection. Okay? Now, yeah.
What if you remove the points at the end?
The point at the end?
Yeah, so line segment but without the 2 endpoints.
It's manifold.
Shade down the cone a little bit too, right?
Yeah, well, oh, do you really want to hear this story? Do you really want to hear it?
Why not?
I'll tell you this story.
Okay.
Imagine if you wanted to put physics on a cone. That point sucks, it's singular. Wouldn't it be awesome if the physics that you put on the cone made it do this? Now, in order for this to happen, the physics you're putting on the cone has to say, that's a special point in space. We're going to change it, smooth it out, but we're not going to fuck with anything else, because everything else is fine. Okay? Let's see. Okay, if I wanna do this, and I should actually put this over here, but I was putting it right under for reference. If I want to do this, and you know, I can talk about like particles are going around in circles, or momentum's quantized, and when they get here, they're, I don't know. But a particle can get as close to here as it wants, and it can move away from it. It can go anywhere it wants, right? So particles, they're just not going to do it. What about strings? If my theory involves closed strings, which are loops, then introducing strings to this, there will be a variety of them which can wrap around this point, but cannot move away from it, because the string has a finite length. So I get what are called twisted states of strings, which are localized to this point. The rest of the strings can wander anywhere they want. So by throwing string theory, closed string theory, on this space, I automatically get a set of states which are localized to the tip, nowhere else. And if you take a step back and squint your eyes, that is, you take the low energy limit, it looks like this. But anyway, I don't want to sell string theory.
So that just
That's
remove
shit no one cares about.
singularity?
Huh?
Can you just do that to remove a singularity though?
Can you do it to remove the singularity?
Yeah.
Well, that's the question. So strings can actually live on these singular spaces, but what I'm saying is in the lower energy approximation, where you're basically taking the string length to zero, and you're basically satisfying Einstein's equations. That's the deformed geometry that appears in the low energy limit.
So you just like infinitesimally like shave off the top of that like cone for string theory to like a round point. So that
Well, the strings themselves are doing it. Yeah.
Oh, okay.
So anyway, I don't want to get too. You could ask me lots of string theory questions, to which I would want most of the answers, but anyway, we're not going to get into that today. To answer Joel's question, though, if I remove the ends, it's a manifold. Okay. All right. Okay. So where was I? Shoot, I forgot where I was. Oh, so yeah, we have manifolds and not manifolds. So another way to think of a manifold is it's something which is smooth and boundaryless. So if you think about it, this is not smooth because of that point, and then the boundaries are screwing this up, and that intersection is screwing things up. So manifolds play a very, very prolific role in physics. And one of the huge advantages is that since they're locally, all manifolds look like Euclidean space, then we can always affix a copy of flat Euclidean space to each and every point, which allows us to define vectors on the space. So every manifold allows the definition of vectors on the space. They just live in the tangent bundle to the space. Okay? Notice, the tangent bundle at that point, or the tangent space at that point, I have no idea. The tangent space is at these points, I have no idea. The tangent space is here, it's fine, but at these points it's screwy. The tangent space there, I really got no idea. Is it 1D, is it 2D? I don't know, okay? So, manifolds in general will allow this construction which allows vectors to be defined upon them, okay? Now, so far, in my definition of manifolds, I've only really defined them topologically. We'll get past that in just a minute, but I just want to pause there and say that with our definition of manifold so far being topological, it lets us answer certain questions which are basically topological questions. So for example, consider the following. Consider if you lived on a two-dimensional space, and that space was hella huge. It's as big as the Earth. Okay? And what you would like to do is figure out, do I live on a sphere or do I live on a torus? These are just examples of, there's many examples of two-dimensional spaces, but these are two simple ones. The difference between a sphere and a torus is basically a topological difference. I could induce, something which will tell me about distance, and then I can say this is a big sphere, this is a small sphere, but we don't care about the size of these. We're just asking, are you on a sphere or a torus? And the critical distinction is topological. But I can give you a means of figuring out which one you're on by local measurements, which is a bit weird, right? I mean, how can you figure out the whole entirety of the geometry that you're on just by walking around with like an ammeter? Boom. Okay? Turns out you can, because these emit vectors. So suppose that you had some device which generated a vector field. Plates generating an electric field, I don't really care. Okay? And you set up on your space a vector field. Okay? If you set up a vector space and based on your construction you tried to have the vector field be non-zero at every point, if you achieve that, then you are not on an S2. You could be on a T2. Let's see what I mean. First of all, if I'm creating a vector field on this, then the vectors point in the tangent spaces. So if I just take a walk around this loop, I'll have all these vectors. And I can set up a similar vector. And it's a vector field, if you will, so the vectors live at every point. But obviously, there is a problem point, because at some point, vectors aren't going to happen, okay? In fact, if you look down from this, then your vectors are doing this, and as you get to that point, the vectors have to go to 0. And similarly down here. Okay, so you could walk around with your vector detector.
As one does.
As one does, yes. I got my vector detector in hand and I'm just walking around and shit, man, I can't get it to be non-zero everywhere. Then you might be on an S2. However, if you can get it 0 everywhere, then obviously T2 is a possible space you're living on. Because we can do these in circles, obviously, and then we can go around the entirety of the T2. Okay? Now, that's all I'm going to say about topology. There's plenty more we can say, but I think that's all I'm going to say. But I just want you to be aware that the definition of manifolds as topological spaces can play important roles depending on what questions in physics you're trying to ask. So, what we now want to do is introduce to these spaces the notion of distance. So for a notion of distance, we can first of all remember the old notion of distance. The old notion of distance was if I pick point A and point B in Rn, doesn't really matter, okay? Then I really just, I set up a coordinate system, I take the coordinates of this, I take the coordinates of this, I subtract them, and that gives me the length between A and B, okay? This is obviously going to fail in the sense of curvature, because, if I go to S2, and I pick points A and B, and I ask, what's the distance between them? Well, first of all, you might say, well, connected by a straight line, dude, just like we did up there. Why not? did that straight line go that it's not supposed to go?
No.
Yeah, it went through the non-existent interior of the sphere. This S2, that two-dimensional surface is all that exists. Yes, we're embedding it in 3 dimensions to draw it and experience it because we live in 3 + 1 dimensions, 3 which are spatial. But anyway, but this interior does not exist. So fine, maybe we do this. Okay? Well, I mean, it's not really the distance. Okay. Turns out, figuring out the distance between 2 points is not really a great question. Rather, what we should say is, I've got 2 points in space, and I want to consider a path connecting them. This is a path, call it S. And I would like to know the length of the path between them. And then I might consider another path between them, S prime, which again, that exists on the surface of the S2. Okay? And this will obviously have a different length. So the notion of distance I should really associate with paths between points. Okay? Now there are certain, nice situations where you can extremize the length of the path and define geodesics and all that, but we're not going to worry about that. So in order to do this, what we're going to do is we're going to take a path, S, and we're going to break it up into infinitesimal segments, which we call ds. Okay? And then the length of the full path S is just going to be, as usual, the integral of ds. Okay? So, what is ds? I mean, we're going to do a calculation, we're going to integrate ds, but what the hell is ds? Turns out, to get an expression for ds, we're going to have to label points in the space. And we're going to have to identify, this point versus this point versus this point versus this point versus this point. So we're going to need to coordinatize the space. Okay? So to do so, what we can do is we can take part of the space. You have a question, or are you stretching?
No, I'm very stretching
That's fine.
somewhere, sorry.
We can take part of the space, say everything from here down to here, and we can map it, and I'll call this part of the space U alpha. We can map it with a map phi into R2 in this case. Okay? Now notice, this is not what I was doing here in attaching R2 planes to generate the tangent space where vectors live. What I'm doing here is I'm taking a piece of this space and I'm providing a map from points in this space into R2. R2 because this is a two-dimensional space, that would go into R3 if it was a three-dimensional space, et cetera, et cetera. Okay? In certain cases, I can do this with the entire space. I can always do it with just a patch of the space. However, there are situations where you cannot do it with the entire space. This is an example. You can't actually do this with S2. Because one of the restrictions in this map phi is that you end up in an open subset of Rn in general. Okay? So if I have a map from this subset of the original space into an open subset of Rn, then phi, which is map from U alpha into Rn, is called a chart, not a map, this is a chart. Okay? And now what we can do is in Rn, so in this case in R2, we know that we can just set up a coordinate system. but notice something. This is a basis in R2. This is a basis in R2. This is not defining angles. These are taking values in R2. Now, in order to cover the entirety of this, we would cap these as we would cap these. You wouldn't go to infinity, all right? But this is essentially how we go about coordinatizing this space. We take a patch of it, we map it into Rn, and then we just use coordinates in Rn. And we can use any coordinates that you like, okay? Now, okay, so I've got coordinates. Now, if I want to talk about distances in this space, then clearly I could take the usual notion that, you know, the distance built out of these coordinate differentials is just dx squared plus dy squared, right? But if I alternatively just called the two axes theta and phi, then it would also be d theta squared plus d phi squared. If I'm using this sort of usual notion of the distance in this space as the vector length. Well, I'll just ask you, actually I'll pick a card. I'll just ask Seth.
Yeah.
Is this right?
Only if we don't think of them as polar coordinates.
Yeah, I mean, if I literally just say, oh, I'm going to call x theta and call y phi,
Sure.
then this becomes this, and I'm
Right.
done.
Not,
Yeah, that's not the usual coordinate
Jacobian.
relation, okay?
yeah.
So in order to do this accurately, what we can do is the following. First of all, notice that we can take the dxi's, which could be dx dy or d phi d theta, and we can consider these as the components of a vector which lives in one of these attached tangent spaces. So if I'm at this point and I'm constructing this dxi, this is just going to be a vector in this space. Okay? So what we can do is clearly this involves two vectors. So what we can do is we can sort of expand this story and we can say, okay, fine, that's not quite right. Rather, what I should do is I should say this is the square root of gij times the vector dxi times the vector dxj. Okay? This thing is called the metric. And the metric has built into it all of the funny coefficients that come in these terms. But it is also, in a sense, sort of the definition of distance, hence the name metric. All right? So notice dxi could be dx or dy, or dx and dy, or it could be d theta, d phi. The dxi vectors here are just these coordinate differentials. All of the rest of the stuff which goes into determining a distance is going to be found in this metric. Okay? Now, I'm using index notation. How many of you are familiar with index notation? Raise your hands. Be brave. Okay, so index notation just says I and j take values over the dimension of the space. So if this is a two-dimensional space, then I and j can each go from 1 to 2. If an index is repeated, then I sum over the index. So this thing is really supposed to be G11 dx1 dx1 plus G12 dx1 dx2 plus G21 dx2 dx1 plus G22 dx2 dx2. Okay, that's my really quick rendition of index notation. If you really want to learn it, take my GR class. At any rate, okay? So the way that you can understand this in terms of vectors and matrices, because that's another way to do this sort of manipulation, is you can say, okay, Gij dxi dxj, well, first of all, if I'm going to sum over an index and do it in matrix form, I should put the things I'm summing over immediately adjacent. So I should write this as dxi gij dxj. That way the i's are right next to each other and the j's are right next to each other. And now the way that I can interpret this is I've got a dx vector, which I'm transposing. I've got the matrix G, and then I've got the vector dx. Okay? Another way to say that is I've got a row vector, a square matrix, hitting a column vector. Hopefully it's obvious. This will give you a number, which is what ds ultimately is. It's a number, not a vector. Okay? So, the form of the metric itself, what goes here, depends both on the coordinates you're using and the space you're considering. Let me give you some examples. So, I shouldn't have gone to GD. All right, yeah. Let me consider R2 with coordinates x and y. The metric in this case is, any takers?
Diagonal matrix of ones.
Yeah, I mean, look, this is the standard definition of the, the length of over which dx and dy carry you. So yeah, in this case, it's real simple. What about in the same space, but using theta and phi? Remember, on the sphere, you just have angles, but in R2, you got to have a radius and a single angle. Okay? What would the metric be in this case? So here I'm saying ds squared is simply dx squared plus dy squared. What is ds squared in terms of dr and d phi? Any takers?
Is it 1, 0, 0, r?
Well, this is dr squared plus r squared d phi squared.
Sure.
If for no other reason than the fact that this is a length, this is an angle, so to make it a length, I just multiply by r to get arc. But nonetheless, that makes the metric that. Okay? Any takers for what it is on a sphere? S2 of radius capital R.
Is that theta?
Say it again?
Is that theta?
Theta and phi, sorry. So S2 you can coordinatize by two angles, obviously. You could also do it with XY, but let's don't. Okay? What would the metric be on a two-sphere using coordinates theta phi? Does anybody know what ds squared is on a two-sphere? A radius capital R.
Is it, oh,
How about that? Oops, sorry. R squared. Does that look familiar? What's the metric? It's matrix form.
R squared. Wait, hold on.
r squared d theta squared plus r squared sine squared theta d phi squared. Remember, this should be d theta d phi times the metric times d theta d phi.
squared sine r.
So what are the rest of the components of the matrix that give you this? I mean, if it was the identity, you'd get d theta squared plus d phi squared. You want to get r squared d theta squared, so instead of 1, you put r squared. And then if you want to get r squared sine squared theta times d phi squared, what do you put here?
R squared sine squared theta.
Jeez, yeah. Yeah, 0, 0, r squared sine squared theta. Okay? These are just some examples, but all I want to point out to you is the metric depends on two things. One, the space you're on. Two, what coordinates you're choosing. Obviously, this is the same space, but with different choices of coordinates, I have different metrics. I could use a different set of coordinates for the surface of the sphere, I'd get a different metric. Okay?
If it's r squared there, shouldn't it be r squared in the r2 case? Above.
Oh, sorry, yeah, you're right. Thank you. Now, I want you to notice something. What is the metric in good old R2 in rectangular coordinates? It's this. What is a really big difference between this and these? Can anybody point it out?
Eigenvalues?
Yeah, there's that, but I mean, there's just something fundamental about this matrix versus these matrices.
They're not identity.
Say it again?
R2 is just identity.
That's true, this is the identity, but you know, the identity in matrix language is kind of a weird thing.
Is that the second two are not constant?
Exactly. This is constant. This doesn't care where you are. It doesn't matter what value of x and y you're using. This matters depending on the value of r that you're using, and this depends on the value of theta that you're using. Okay? So if we have a space in general, and we want to define distance, to do so, we're going to have to introduce a metric function, and that metric function might be a function of where you are. It might not, but it might be. And notice, just because you're in flat space doesn't guarantee that the metric is a constant. If you choose coordinates which are not rectangular, your metric won't be constant. Okay? Does this make sense? All right. So we can finish up calculating the distance s by saying, all right, well, first of all, let me give this some bounds. So I'm going to start at the point SI, end at the point SF. And then what we can do is we can say, okay, in order to describe the contour via coordinates, what I can do is I can just parameterize my path through the coordinates by some parameter. I'll say it's lambda. So at lambda equals 0, I'm at SI, and at lambda equals 1, I'm at S final. So this might be time, if you're weird enough, okay? So we can say, okay, this is the integral of the square root of gij dxi dxj, but the dxi and the dxj, I can take the derivative with respect to the parameter of the curve lambda, and doing so, I can say, fine, this is square root gij dxi d lambda dxj d lambda integrated over with respect to lambda. Okay? Now clearly, the distance along a contour, yes?
So lambda's a real parameter. Xi, is that's actually a point inside of the flat space that we mapped to?
Yes.
Is that true? Okay, cool. Great.
So, clearly, yeah, that's what I was gonna say. The distance along this path should be coordinate independent. So there's a certain sense in which this expression for ds, or just in general, we might say ds squared, is the way we usually represent it. This infinitesimal distance should be coordinate invariant. Okay? And next time we're going to explore what kinds of transformations we can do which will leave this invariant. What I'm going to finish with now, though, is sort of a extension of this distance story to another way to interpret it, which will hopefully make some contact with what you've seen in relativity. And just to drive the point home. One way to imagine interpreting, and in my notes I put mu nu, but I'm translating it to ij to be spatial for all of you, but you could interpret mu nu as spatial indices as well, but at any rate. So this is a measure of distance. This is what we would call ds squared. We just say ds squared, so we don't try to square root over everything. That's ds squared. Another way to interpret this is that this is dxj, where the dx with the lower j is the dual vector corresponding to dxj. Now, I'm not going to spend a lot of time on duals and dual spaces and so forth, except in this context, but if you think about it, if you have a vector space and then you define a dual vector space, then one of the means of defining a dual vector space is that you can take an element of the dual vector space and naturally combine it with an element of the vector space to produce a number. Okay? So what's critically important is that this thing is not a vector. It is a different quantity. We'll just call it a dual vector. We say dual because for any given vector, you can find its dual. That's the name dual. I mean, I could obviously take two vector spaces, two entirely different vector spaces, and I can label a vector in this one, I can label a vector in this one. They might not have a damn thing to do with each other. But here I'm taking a vector space and a dual vector space, and I'm saying every vector in the vector space has a corresponding element in the dual vector space. In fact, we can construct that. We can say that dxj is gji dxi. That is, to create a dual vector, construct the dual vector in correspondence with the given vector, we just apply the metric. Notice how the indices kind of work out. You got overall lower j here and an overall lower j here. The i's are summed over. Boom. Nice. Pretty. Okay? So one way to think about a metric, it's just a map from the space of vectors into the space of dual vectors. But, you know, what if I say, okay, fine, dxj is gji dxi, but, you know, dxi should be something involving g, and maybe it's, you know, that. I mean, you know, I should, if I can construct dual vectors from vectors, I should be able to construct vectors from dual vectors. So all I've done is I've just, you know, set up an index consistent version of that story. The vector dxi comes from the dual vector dx alpha by the application of this thing. But what is this thing? What is this thing right here?
It's the identity,
Well, what does this
right?
need to be?
It's the identity.
Well, this needs to be dxj, because that's what I started with.
Yeah.
So that means that this right here should be delta j alpha. Because if I take delta j alpha and I combine it with dx alpha, that's just going to take the alpha and turn it into a j. This is a delta function. It's 0 if j is not alpha, it's 1 if j is equal to alpha. So this is just gonna take this and turn it into dxj. But what I'm saying is that the metric times this gives me the identity. So what is this?
The inverse metric.
It's the inverse. So g upper mu nu is simply the inverse of the metric. Now you want me to show you where it gets screwy? Check this out. In R2, with coordinates x and y, the metric 1, 0, 0, 1. What's the inverse?
Same as these.
If this is the space you're working with, you never really worried about whether it was the metric or the inverse metric. Who cares? What if you're using polar coordinates?
Totally matters.
It's different, right? With polar coordinates, the metric is 1, 0, 0 r squared. The inverse metric, 1, 0, 0, 1 over r squared. Okay. All right. Just to finish up, these things are not vectors, they're dual vectors. Where do they live?
In the dual space.
That's close enough. They live in what is called the cotangent bundle. Okay? So just like to have vectors in the space, we had to be able to build that vector bundle over the space, which we know we can do for a manifold. We can similarly, at each point in the space, construct a cotangent space, which is where the dual vectors live, and then the collection of all of those cotangent spaces is the cotangent bundle for the manifold. Okay? All right. So now that we have a little bit about geometry and vectors and their duals, next time we'll talk about what kinds of transformations are going to leave this story consistent. And that will get us into the algebras. More on that next Thursday, not next Tuesday. Remember, we don't have class on Tuesday.
Do we not have classes generally, or
Say it again?
do we not have classes at all next Tuesday, or just not?
No, it's just the class.
Okay.
I'll be away, so. Thanks you all for coming today. I do appreciate it.